Welcome to the second part of the optimization lecture. Now, in the first part, we have discussed the unconstrained optimization of a function. So we are given one function and we just want to minimize it over the whole domain. And now we want to discuss what happens if we restrict the set of feasible solutions by another set. So let's consider a more complex setting. Now we introduce constraints. Okay, so a constraint optimization problem is given as follows. We have our objective function and some constraint function ci and gk. And then the general form of an objective for a constraint optimization problem is given as you can see here. So we want to minimize again our function, but now subject to some of these constraints. And you can see that these constraints are distinctive by the equalities which they have to satisfy. So for the functions ci, we have here equality requirements, and for the function gk, we have here an inequality requirement. And we call them the set of vectors which satisfy the constraints, the feasible set. So this is the set of all the vectors x for which the constraints hold. How can we now solve such a constraint optimization task? We have seen that for the unconstrained case, we can solve or find the local minimizers by Fonck and Song. But that doesn't help us now anymore much, because if you have a function and you have some constraints, so you say that, for example, you only want to consider the values which are in this interval here, then Fonck and Song would tell us that we have a local minimum here and here and here. We can have a look at these local minimas which are inside the feasible set, but we also have to check what happens here at the boundary, because there could also be local minimas which are not discovered by Fonck and Song because they don't know about the constraints. Now here in this example it's not so super complicated, so we can just apply Fonck and Song to our function, and then we could check at the boundary what the function values are and if they are actually smaller than the local minima we get by Fonck and Song. But in optimization problems, which we will discuss in this lecture, we will have a feasible set where the boundary is, for example, a whole plane. So you cannot just go through all the points in the boundary, but you really have to find a mechanism which tells you what happens at the boundary, so to speak. Now, the idea of solving a constraint optimization problem is to transform the constraint problem into an unconstrained one. But this is like a big topic of itself, so here we will just uncover the intuition behind this approach. I said here, yeah, can we transform the constraint problem into an unconstrained one? Yes, maybe, kind of. Because there are a lot of requirements for which we will not have the time to explore them in detail, and also it's quite technical. So we will introduce here the concept of the Lagrangian and the intuition behind it, and then if we use it during the lecture, then you can build upon what has learned here and then just go where you need to go to understand this particular instance of the Lagrangian function application. Okay, so let's have a look how that goes. Given any constraint optimization task, the Lagrangian function is then defined as the function L, which maps from our vector x and two other vectors lambda and mu. It takes the objective function value and it subtracts the sum over all weighted constraint functions. And the lambda i's and the mu k's are here the factors for all of these constraints, and they are called Lagrange multipliers. And for the functions which are modeled to reflect inequality constraints, we will have to require that the corresponding Lagrange multiplier is non-negative. Okay, so this is just a definition of a Lagrangian function. And why the Lagrangian function is interesting is because it forms a lower bound of the objective. So if we have a vector x which is in the feasible set and the vectors lambda and mu, we have that the Lagrangian function, which is defined here as we have learned it in the previous slide, is actually always smaller than equal than f from x. And this is easy to see because for feasible x, we have that our constraint ci from x is equal to 0 and the constraint gk is larger than equal to 0. And here you also see why the corresponding multiplier has to be larger than equal to 0. Yeah, to keep this whole term then larger than equal to 0. So we have here f from x, and then we subtract something which is equal to 0, and then we subtract something which is larger than equal to 0, and then we get, of course, something which is smaller or equal to f from x. And if we want to minimize f, then this is interesting, because we get therewith a function which is a lower bound. So it basically gives us a lower bound of the minimizers which we can find. And therewith we get then the dual objective function, L dual, and the reasoning goes as follows. So if we want to find our minimum from f from x, then we know that it is larger than equal to the infimum over all feasible points from our Lagrangian function. And then if we relax this constraint and we say, okay, x has not to be feasible anymore, but x can now take any value, then we can find even a lower infimum. So if we have here our feasible set, so this is C, and we have the space of R to the power of D. If I try to find my minimum now within the feasible set, then I can find even a lower minimum outside of the feasible set, because it's just the feasible set is contained in the larger space R to the power of D, right? So our minimum from f from x over the feasible set is larger than equal to the infimum of our Lagrangian function, and this infimum over all the points in the domain R to the power of D is now defined as the dual function. And the dual function depends now only on the Lagrange multipliers, so the vector x and its constraints are not there anymore. And this is why this is a potential mechanism to formulate a constraint optimization problem as an unconstrained one. Because for lambda and mu, we basically don't have any restrictions. We only know that mu has to be non-negative, but this is not such a very difficult restriction, so we can handle this. And this gives us then the primal and the dual problem formulations. So the primal problem is basically how we would state this as a constraint optimization problem, and the dual problem is to find now the maximum of the dual function such that lambda is in the real valued vector space and mu has to be a non-negative vector. So if we look back, here we had the minimum of f is lower bounded by the dual function, and if we then maximize the dual function, then we get close to the minimum of f. This is the intuition behind the formulation of primal and dual problems. Now the solution to the primal problem is always bounded below by the solution to the dual problem. This is what we have derived in the previous slide, and this becomes particularly interesting if we have that the solution of the primal problem f star is equal to the maximum solution of the dual problem. Then solving the dual is equivalent to solving the primal. But these conditions, this is where it gets a bit nasty. This is where it becomes a bit gritty, and which will be then only discussed for particular cases during the lectures when we need it. Okay, so if I have an unconstrained optimization problem, then I try Fonck and Song to get the local minimizers analytically just by calculating around. And if I have a constrained optimization problem, then I can try to solve it over the dual problem. We don't know yet how exactly, but I mean that this can be then discussed. But we have an idea how to approach this. But what if I can't compute these minimizers by any of these approaches? Well, then we fall back to numerical optimization. Now, if the minimizers cannot be computed directly or analytically, then numerical optimization can come to the rescue. And the general scheme of numerical optimization methods is an iterative scheme. So I start at some point on my valley, like if you think about this mountain, you just start somewhere on this mountain. This is your initialization point. And then you take iterative steps, T max steps. And in every step, you update your current solution. So this is basically you start at your mountain, and then you take one step, and then you take the next step, and in every step you might go into a different direction such that you can go down the most quickly. And then after like some stopping criterion is satisfied, so here we specify a number of maximum steps with Tmax, then we return our current iteration, so we return where we are standing right now on this mountain. Two of the most popular versions to do that is coordinate descent and gradient descent. Coordinate descent is for the cases when we cannot say where the local minimas are by Funk and Song, for example, but we can actually derive the minimum in one coordinate direction. So this means that we fix all of the coordinates except for one and try to find then the minimum with respect to one coordinate. So we have here these coordinate descent-wise updates. The coordinate is here identified by the index I. So the ith coordinate is updated in step t by this update rule here, where we find the argument of the minimum when we fix here all these coordinates from the previous steps, and we just optimize subject to one coordinate. And because we minimize in every step, we actually get a non-increasing function value sequence. So in every step we get a bit lower, or we stay with our function value where we have been. And how this looks is here visualized on the right. Our initialization point is here at x1, x0. And now we fix x1 and we only optimize subject to x2. And then we go here. And then we fix x2 and we optimize only subject to x1. And we get here, and then we are actually here in our minimum. For example, we can do this with the Rosenberg function. If we fix here x2 and we optimize only subject to x1, then we can apply Fonk to find, for example, the optimum in the coordinate x1. This is then like a one-dimensional function, and then the minimizer is actually equal to 1. And for x2 we can do the same, and then we get that x2 has to be x1 squared. And this looks then as described here. So I start here at this point, and then I optimize subject to the first value x1. And then you see here that we have the 1 here. So x1 is set to 1. And then we also set x2 equal to x1 square, so this is 1 square. So we arrive here at our minimum 1, 1 after 2 steps. Now if that does not work either, so if it's difficult for us to derive the argument subject to one coordinate, then we can apply gradient descent. For gradient descent you basically just need a gradient, and this is in most cases derivable. And then the update is that you subtract the gradient scaled by a specified step size. Yeah, the step size is really like if you're at that mountain and you take a step, and then you can take big steps or you can take small steps. And the negative gradient actually points into the direction of steepest descent. So you always go into the direction where locally, if you just look down, that you see that, okay, here it goes down the most. So if we take a small enough step size, then we always go down a bit. And then we have again this at least non-increasing sequence of function values. And the visualization is given here. So I start x0, and then I take one gradient step, then I take one gradient step, then I take one gradient step, and then you see that after a sequence of steps we arrive here at the minimum. Okay, let's see how that works for our Rosenberg function. So here we have a step size eta, and we start here on the left, and then you see here we take a bigger step. So this might be because the direction is very steep from this point here, so then the gradient is big, so to speak. And even if we have the same step size, then it might look like we take actually larger or smaller steps. So the first step is big because the gradient is big, and then it goes here down and down and down, and you see it goes smaller and smaller because the closer we are to our optimum, the smaller the gradient becomes. Like at the optimum our gradient is 0, so around the optimum the gradient is also approximately 0, so here we take very, very small steps. Then you see that we actually need here 2616 iterations if we choose the step size like we set it here. Now what happens if we take a bigger step size? Okay, then we go here a bigger step into this direction, then we go in this direction, and you see that it's a bit zigzagging around, right? So this is the effect if you have a too big step size. Then actually sometimes it might not converge, because you could, for example, if you take two big steps, then you can go up your function. Like you go always in the direction of the steepest descent, but you go so far that you're already beyond like where it went down. And here we try it with an even smaller step size than from the first slide. And there we see that, yeah, you need really a lot of iterations. So it's 6,628 iterations. And it goes here directly very soon into this valley where not much is happening in terms of curvature. So the gradient here is extremely small. Yeah, and then with tiny baby steps, we go here to our minimum, but yeah, it takes a long time. So you see the step size actually has quite the impact on the result. Now the thing is that with every run of numerical optimization, I get one minimizer candidate. But how do I know if I can do better? With Fonk and Sonk we got a set of all possible minimizers, but here I get just one. So how do I know if this is a good one? And the answer to this is analyze the optimization problem. And then in the next in the next part of our lecture, we will discuss for one class of optimization problems for which we can actually say that if we found a solution that it cannot get any better. See you then.